so good morning everyone. So today we have presented the experiment 7, which is the estimation of the heat capacity and the entropy generations, which is the open-ended experiment. So for the introduction part, what is the heat capacity? Actually, heat capacity is the amount of the heat energy that required to rise the temperature of a substance per unit degrees. So substance with a higher heat capacity inherently require more energies to change their temperature. So they go the two variations of the heat capacity. The first one is the specific heat capacity, which is the C. The heat capacity normalized per unit mass of a substance. So the SI unit for the specific heat capacity, which is the joule per kg per kelvins. And another one is the molar heat capacity, which is the CMs. So the heat capacity normalized to exactly 1 mole of substance. The SI unit for the molar heat capacity is the joule per mole per Kelvin. So for the applications of the heat capacity, actually we are using the heat capacity in the heatings and the air conditioner, which is the HVAC. So for the entropy change, the entropy change of a system during a process is equal to the net amount of the entropy transfer or heat across the system boundary and the entropy generated within the system. So actually the entropy change is not just a theoretical concept, it governs the efficiency of engines, power plants, and the biological system you interact with daily. So for the application of the entropy plan and the entropy change which in the chemical reactions and the safety, the energy storage, the material design, and the power generations with the Rankine cycle. So for the objective for our experiment, which is to estimate the heat capacity C or different providers matter. Also to estimate the entropy generation, the delta S when heat metals are dropped into a speaker containing water. And for our scope of the experiment is the experiment utilized 3 distinct metals, which is the irons, aluminiums, and the copper. So the temperature depends on this property will be analyzed across operational range spanning from the room temperatures up to the 60 degrees Celsius. And the water acts as the coolants in this experiment.
For the theory part, specific heat capacity is the energy required to raise the temperature of a unit mass of a substance by 1 degree as the pressure is maintained constant. When a hot metal is being dropped into a cooler water, which is in room temperature, heat from hot metal will be gained by the water. Initial and final temperatures for both water and metal being measured, so the metal's specific heat capacity can be estimated using the formula while knowing the water's specific heat capacity. So the specific heat capacity at 25 degree of water is 4.186 kJ per kilogram Kelvin. Copper is 0.385 kJ per kilogram dot Kelvin. Aluminium is 0.897 kJ per kilogram dot Kelvin. And iron is 0.5450 kJ per kilogram dot Kelvin. The general formula for specific capacity is given by Q equal to mCp delta T, where Q is the heat energy transferred kilojoule, mass M is the mass of substance in kilogram, Cp is the specific heat capacity of substance kilojoule per kilogram dot Kelvin, delta T is the change in temperature, either in Kelvin or in degrees Celsius. So the first law of thermodynamics, for a closed system, the general energy balance can be written as Q minus W equal to delta U, where Q is the heat added to the system, W is the work done by the system, and delta U is the change in internal energy. For this experiment, there is no work done, W equal to 0, hence Q equal to delta U. The heat lost by the hot metal is equal to the heat gained by the water, where Q lost metal equal to Q gain water. So if Q greater than 0, heat is being absorbed, which is going through endothermic process. When Q less than 0, heat is being released, which is exothermic process. Q metal is less than 0, which means heat released by the metal, and it goes through exothermic process. Q water is greater than 0, heat is being absorbed by the water and going through the endothermic process. So the formula is Q lost metal equal to Q gain water, which is M metal times with Cp metal times with temperature metal initial minus with temperature final equals to mass water times with Cp by water, and then T water times with T water initial.
Okay, so this is our experiment setup. So our experiment has a metal steel thermometer, amplified stopwatch, water container, beaker 1 and beaker 2, and iron broke, aluminium broke, copper broke, and a hot spread and electronic balance. So next is our methodology. So first, the copper block was weighed using the electronic balance, and the weight of the copper block was recorded in table 1. A second, water was poured into beaker once until the copper block was fully submerged. And third is a second beaker was prepared, and the 90 millimeter of water was poured into it. And four is the bigger one of water was heat using the hot plate. And next is the copper block was allowed to heat in the water until the water in the beaker reach a temperature of 60 degrees Celsius. And next, the initial temperature of the water in the second beaker was measured using the thermometer, and the initial temperature of the water was recorded in table 1 also. And next is the temperature of a water in first beaker was measured using the thermometer. When the water in the first beaker reached 60 degrees Celsius, and the copper block was immediately transferred into second beaker. And next is the second beaker was covered with the aluminum foil. And next is the temperature of the water in the second beaker was recorded every 10 seconds until three constant temperature values were recorded. The next and lastly is step 1 to 10 were repeated by replacing the copper block with aluminum foil and iron blocks.
So for experimental result for experiment 7, we got copper mass of which is 38 gram, aluminium 14.4, iron 107.7, and the mass of water is 82.6. So the initial temperature of water is 37.5 for all the three beaker, which is copper, aluminium, and iron. And we get the temperature for 3 times until we get the constant temperature. And the equilibrium temperature for copper is 28.6, aluminium 28.3, and iron is 30.2. Specific heat capacity for copper is 0.1, aluminium is 0.222, and the iron is 0.2919. For the entropy change of metal, delta S, we get for copper, we get negative 0.001. For aluminum, we get negative 0.0008. And for the iron, we get negative 0.00296. And for the entropy change of water, delta S, we get for copper 0.0012. For aluminum, we get 0.009. And for the iron, we get 0.0031. And total entropy generated delta S for copper is 0.00006. For aluminum, we get 0.00004. And for the iron, we get 0.0015. And the equation we use for calculate, which is M, mass of metal, times with Cp, we times with T metal initial minus T final, and equals to mass of water, Cp water, and we times with T final minus T water initial. And as for the Cp, we want to get Cp for metal, so we mass of water times C of water times Tf minus Tw initial over mass of metal times temperature metal of initial minus T final. And percentage error we get which is for the copper we get 73.9, aluminium we get 75.2, and iron we get 35.1. Okay, so this is the graph comparison of the theoretical and experimental specific heat capacity CP of different metal. So for copper, the experimental CP, which is 0.1 kilojoule per kilogram Kelvin, is lower than the theoretical CP, which is 0.385 kilojoule per kg per Kelvin. So as for the aluminium, the experimental CP is 0.222, is lower than the theoretical CP, which is 0.897. For the iron, the experimental CP is 0.292, is lower than theoretical CP, which is 0.45. So iron give the best smallest percentage error, which is 35.1, while aluminium give the largest percentage error, which is 75.2. The differences between the experimental and theoretical value may be due to heat loss to the surrounding, temperature measurement error, and incomplete thermal equilibrium during the experiment. So based on the percentage error analysis, iron produced the most accurate result among the three metals, as its experimental specific capacity was the closest to the theoretical value. So as for discussion, so first is source of error and improvement. So the source of error is which one is heat loss to the surrounding. Second, delay during the metal transfer. Third, temperature measurement in accuracies. Fourth is incomplete thermal equilibrium. So the method like how to minimize the error, which is the first one, we can use an insulated calorimeter. Second, transfer metal quickly into the water. And the third one, stir water continuously and use a calibrate thermometer. So for the second question is important of stirring. First, we need to ensure the uniform temperature distribution. Second, we can prevent hot and cold spot in water. Third, help achieve thermal equilibrium faster. And fourth is improve temperature measurement accuracy. So the last discussion is important of quick transfer of hot metal. First, we can reduce the heat loss to surrounding, maintain actual metal temperature, improve accuracy of heat transfer calculation, and reduce percentage error.
So moving on to the conclusion part, the experiment successfully determined the experimental specific heat capacities and entropy changes of copper, aluminium, and iron using the principle of energy conservation. The experimental specific heat capacities obtained were copper 0.1 kilojoule per kilogram Kelvin, where theoretical is 0.385 kilojoule per kilogram Kelvin, aluminium 0.22 kilojoule per kilogram Kelvin, and theoretical is 0.897 kilojoule per kilogram Kelvin. Iron 0.292 kilojoule per kilogram Kelvin, and theoretical 0.45 kilojoule kilogram per kilogram Kelvin. All experimental values were lower than the theoretical values, and iron gave the most accurate result with the lowest percentage error, 35.1%, while aluminium had the highest and copper had 73.9%. The differences were likely caused by heat loss to the surroundings, temperature measurements error, and incomplete thermal equilibrium. Overall, the experiment successfully achieved its objective of determining and comparing the specific capacities and entropy changes of copper, aluminium, and iron. So, for the safety procedure is firstly thermal protection, where we use gloves to touch the hot surfaces in order to prevent injury or blisters. Second is clean environment, where we keep the experimental area clear of clutter to avoid accidental bumps or spills. And lastly, lab attire, where we have to ensure lab coats are buttoned and close to shoes were worn to protect skin from spills or accidental bumps.